On page 3 in the notes, going to be doing more of what we did yesterday with rewriting logs in exponential form and rewriting exponential form in logarithmic form. So starting with problem C, we've said that if we want to evaluate a single log or a one-log expression, we simply put it in exponential form. So if you haven't already thrown equals x onto all of these, because when we use our mnemonic device, the elephant holding the log in his trunk and his big animal ears, we gotta have the equals x because that's gonna be the exponent in our expression. So then writing the parts of exponential form, the base will be 3, the exponent will be x, and the answer is 1/9. Now, you may be looking at that going, off the top of my head, I'm not really sure how I can get 1/9 from base 3. How can I give that 3 a bad attitude and send it downstairs? Gentlemen!
Oh, yeah. Negative exponent.
A negative exponent. So how can I get 3 to be 9? 3 squared would give me 9. So if I want to get a 9 in the downstairs, it would be 3 to the negative 2. So then x is equal to negative 2. So moving on to problem D. We see the word log and we think of the elephant with his big animal ears. So 16 is our base. The exponent that goes with that base is x. And our answer is 4. This one I think is a little bit harder to solve intuitively. So this brings us to what we're going to be doing in a couple of days. In order to solve an exponential, it's easiest if we can write them as the same base. Can I write 16 as base 4? 16 is the same as 4 squared. So if I have 4 squared raised to the x equals 4 to the first, what do we know about those exponents? They would have to be equal to each other. So 4 to the 2x equals 4 to the first. The bases cancel, and we get 2x equals 1, or x equals 1/2. So that goes into our strategy for solving exponentials, because if we can rewrite both sides as the same base, like base 4, then we can cross off the bases and set the powers equal to each other. But going back here, does it make sense that 16 to the 1/2 power is 4? Taking something to the 1/2 power is the same as doing what? Square rooting. So 16 to the 1/2 says the square root of 16 is equal to 4. So some of you might need to show getting the same base. Others might be able to look at that and say, hey, I can take the square root of 16 to get 4, so that would be to the 1/2 power. Let's go ahead and look at the next one. We see the word log and we think of the elephant with his big, what's our base on this one? When there's no base explicitly written, our log is the common log or base 10. So just like a square root has an implied index of 2, common log has no base written, but I'm going to go ahead and throw in that base of 10. That way when I do my big animal ears, the 10 is my base, the x is my exponent, and this is equal to 10,000. So 10 times itself, how many times is going to give me those 4 zeros? 4. So 10 times itself 4 times is going to give me 10,000.
Where'd you get the 10 from?
So we put in that base because it's implied. So if I just have a log without a base written, base 10 is what we put in. Just like with a square root, when we did power divided by index, we put in that index number of 2. So then on this one's a little bit weird because it is in logarithmic form, and we're going to put it in exponential form to solve. Similar to how we put the base 10 in for the common log. I'm going to actually write common log by that one. Common log is base 10. This is the natural log. ln is the natural log. And ln is the same as log base e. So I have log base e of e to the third equals x. Then when I rewrite it in exponential form, that's my big, that's my animal, and that's my ears. So base e raised to the x equals e to the third. We don't even know much about what e is equal to, but based on our common parts here, what do you think x is? It has to be 3. When I have the same bases, we can cross them off and set the powers equal to each other. So x equals 3. So how do we solve a 1 log expression? We put it in exponential form. Natural log is log base e. Common log is log base 10. We're now going to go into the guided practice. And I want you to turn to page 2. And you can cross off 17 through 19. So cross off 17 through 19 in the guided practice. I'm not going to do any of those. And we're going to work on 20 through 23 and 24. Not 24, just kidding. Skip that one. Actually, 27. 27, not 24. So I want you, best you can, to try 20 and 21. Writing those in logarithmic form, just rewriting, nothing to solve for there. 22 and 23, writing in exponential form. And then see if you can evaluate number 27. If it helps, you can put an equals x onto the end. Good luck. So what I would do on that one is try to get them both as base 3. I can't rewrite this as base, but I could rewrite 9 as 3 squared. But since I want 1 over 9, it would be the negative power. Then we can cross out the bases and say x is negative 2. Yep. All right, so for the first few, writing in logarithmic form, there's my base, there's my exponent, there's my answer. So we write the word log and we think of the elephant with his big base 2. Animal, 32 for the answer part, and then ears equals 5. And remember, to say that, log base 2 of 32 equals 5. Log base 2 of 32 equals 5. Raise your hand if you got that one right. Super duper. Then for the next one, That's my base, that's my exponent, that's my answer. How do I know that that's an exponential form?
Because you can tell.
Because it's got an exponent. Easy peasy. So then to write it in logarithmic form, log, and then the elephant. Big, base 10. Animal, 1,000. Ears, 3. Now, when we write it in log form, we do want to write it in the easiest way possible. So since this is log base 10, we can replace that with just the common log notation of just log. The 10 is implied. And then equals 3. So that would be our best way of writing that expression. Now to go in the other direction. How do I know that 22 and 23 are written in log form? Because it says log. We've got log base 7 of 343 equals 3, and we have natural log of 18 equals y. So we see the word log, we think of the elephant with his big animal ears. Our base is 7, our exponent is 3, and our answer is 343. Is that legit? Is 7 to the third 343? So when you write in exponential form, you should be able to tell or try it on your calculator to verify that you have gotten something true. Now for this one, we have natural log of 18 is y. So what's my big? Well, let's go ahead and replace natural log with what it is equal to, which is log base e. So log base e of 18 is y. We write it as log base e so that when we do our big animal ears, we can clearly see that our base is e, our animal is 18, and our ears is y. So e base raised to the power of y is 18. Raise your hand if you got that one right. That one was a bit tougher. You're doing good. How are you feeling about logs so far?
Weird.
They're weird, but not so bad. Lots of rearranging and rewriting. Let's go ahead and take a look at this next one. If I wanted to write this in exponential form, because that is how we evaluate one log, first, we're going to rewrite it. What's the base of this log? 10. So that is our common log since there's no base explicitly written. So we replace it with base 10. Then log, big, animal, ears. And we get 10 to the x equals 1 over 10. Folks, how am I going to write 1 over 10 as base 10? 10 to what power gives me 1 over 10? 10 to the negative 1. So then we can cross off our bases. And x is equal to negative 1. Huzzah.
When you're crossing off the bases, like, what's like the operation you're doing?
So that's a good question. There's nothing algebraic about doing that. We're just kind of comparing common parts. So like if I said square root of x equals the square root of 5, I would be able to say that that's 5 because it's the same stuff on both sides. I've got a square root of something else. I used to draw a little picture of Mario, like next to the little question mark box. It's like Mario to the question mark box, Mario to star power. What does the question mark box have to equal? Star power. Any of you guys play Mario games? No. Anyway, so we aren't doing anything algebraic here. We're just saying, hey, if this is 10 to the something equals 10 to the negative 1, that something can only be equal to negative 1. That was a great question. So, folks, we're going to go ahead and we're going to go back to the notes. Tell yourself I can do this. Tell your neighbor that they can do it. Because graphing logs, it's a little bit nasty. Yep. Now, the first thing that's not super great about logs is, can we check them on our calculator? Not unless it's base 10. There's your common log button, or natural log, which is base E. And you know what? Let's just go ahead and take a look at what the graph of both of those looks like. So I'm going to go ahead and do common log x. So I hit my log button. And then I'm going to do natural log of x. Let's just see what these graphs look like. Oh yeah, and your calculator doesn't do a super great job. So it's tough to tell, but these graphs are both leveling off at a vertical asymptote. And what's interesting about logs is they are inverses with exponentials. So let's just do a little review of what we did yesterday with exponentials. So let's say I've got the exponential equation. Y equals 2 to the x. What would I put in the x column to graph that? What are the easy things that I like to plug in for x? -1, 0, and 1. Those are those happy power values. Why are those easy to plug in? You guys can't see that. There we go. So we are on page 2 in the notes. And what is nice about those power values, we, for the most part, can evaluate them without our calculator. What's 2 to the -1? 1/2. What's 2 to the 0? 1. And what's 2 to the first? 2. So fairly easy points. What else do we know about exponentials? They have a horizontal asymptote at y equals 0. So that's all of our exponential stuff. The thing with exponentials is that these are actually inverses of log functions. We've kind of seen how they're a rearrangement of each other. So going back to the last unit, we can rewrite radical form in rational exponent form, our radicals and exponents inverse operations. How do I get rid of a square? You square root. How do I get rid of a square root? You square it. How do I get rid of a log? You use exponents. How do I get rid of an exponent? We can use logs. So they are inverses of each other. Does anyone remember what finding an inverse meant back in unit 3? What does that word inverse make you think? Opposite. What do we switch around or invert or make opposites between inverse functions? We switch x and y. So I want you to write that exponentials are inverses of logs, which means we switch x and y. And this has some important implications on what's going to happen with these logarithmic graphs. So logarithmic, that is how you spell it. So if I had the logarithmic version of that equation, we would have y equals log base 2 of x. Just using what we know about this table, if I wanted to find a table of values for the log function, we could literally just switch all of the x, y coordinates. 1/2 -1, 1, 0, 2, 1. I took all of the x, y coordinates in this table and I flipped them around for our logarithmic table. Now, how I used to teach this to actually the pre-calc kids is in order to graph logarithmics, we would find the exponential, then we would invert it, and then we would apply the transformations. It was kind of a hot mess, so I'm going to show you what I have found since my last couple years of teaching it this other way, something that makes this easier. Instead of inverting the table, what we are going to do with that logarithmic equation is the same thing that we've been doing anytime we see a log. Put it in exponential form. So if I want to put that in exponential form, 2 is my big, x is my animal, what's my ears? The y. So 2 to the y equals x. That is that logarithmic equation in exponential form. Doesn't that really just look like the inverted version of my exponential equation? Doesn't it look like we literally just switched x and y around? Yes. So instead of finding the table and switching it, we're just going to use the exponential form of the logarithmic equation to graph. So it's actually going to be the same strategy that we used before. We want to try to get the exponent to be those easy values. So I'm still going to use -1, 0, and 1, except what variable am I going to plug in for? The y value. So I plug -1 in for y. 2 to the -1 is 1/2. I plug 0 in for the y. 2 to the 0 gives me 1 for the x value. 2 to the first gives me 2. So by putting it in exponential form, I can do the exact same thing that I did with the graphing yesterday. So it'll be more like a review instead of trying to do all that transforming the table stuff that we did back in Unit 3. The only thing that we are going to have to do by hand using transformations is the asymptote. Now, exponential functions have a horizontal asymptote at y equals 0. Logarithmic functions have a vertical asymptote at x equals 0. So literally everything flips. X and y flip. We go from a horizontal asymptote to a vertical asymptote. That's why logarithmic and exponential functions are just disturbingly similar. It's because they are inverses of each other. So these steps that are written, we're not going to use those ones. You can cross them off as much as you please. And instead, we are going to do the following steps. Step 1, to graph logs. To graph logs. Come on, Zoom. So to graph logs. Step 1, state the transformations and find the asymptote. And what you'll notice is that is almost the same step as what we had for exponentials. State the transformations, find the asymptote. Except we won't have any growth or decay functions for logarithmics. That's just an exponential thing. Step 2, isolate the log, then put in exponential form. Step 3, turn to x equals equation and use power values. In my opinion, graphing logs is one of the more challenging things we do in this chapter, graphing in general. So we're going to see these steps in action on the very first problem. Step 1, stating any transformations. What's the log doing? The log is what makes it a logarithmic function. What's the 5 doing? The 5 is actually doing the same thing that it did for exponentials. It is just the base. So there are no transformations. So if there are no transformations, our asymptote will be at the starting value of 0. Does it go this way or does it go this way? You want to know my dumb way of remembering the asymptote? You know, a log is like a tree. We can draw a little palm tree. It's maybe in the jungle with our elephant with his big animal ears. And oh man, that's a terrible palm tree. Draw a better palm tree than me. That little tree is a log vertical asymptote. There you have it. That's how I remember when that's the vertical one. Wow. Exponential function having a horizontal one, you're going to be able to check that on your calculator. You're going to be able to plug in points and see that it's leveling off. But this one, you have to just memorize. So logarithmic functions have a vertical asymptote. So if there are no transformations, where's that vertical asymptote going to be? Vertical through what point? 0, 0. Vertical asymptote at x equals 0. So remember, Vex and Hay, vertical lines are x equals equations, horizontal lines are y equals equations. So no transformations, vertical asymptote. Step 2, isolate the log. There's nothing more to do to isolate the log in this equation. So we can just put it in exponential form. So we see the word log, and we go in the order right after the log of big, then animal. So what's our ears? F of x. Do we want to use f of x? What's another easier way of saying f of x? Y. So we're going to let y be our ears. So when I rewrite this in exponential form, I get base 5 raised to the y equals x. So same equation, different form. Is that an exponential equation? It's kind of tricky. It's in exponential form, but since x is not in the exponent, this is still a logarithmic equation, even though it is in exponential form. So folks, from here, we follow our same rules as yesterday. We say, you know what my favorite values to plug in for exponents are? -1, 0, and 1. So in our y column, we are going to plug in -1, 0, and 1, the power values. And we're going to plug in the the y values to get the x values. So what happens when I plug -1 in for y? What's 5 to the -1? 1/5. Take it to the downstairs. Bad attitude. What about 5 to the 0? 1. What about 5 to the first? 5. And then we just plot those points. So 1/5 -1. 1, 0, 5, 1. But now instead of leveling off horizontally, we're going to be leveling off vertically towards that asymptote going down and then going outward like this. So if you turn it sideways like this, it should look like an exponential function. And that's the same as swiveling it over that line y equals x, which is what we did back when we did inverses in the previous unit. Previous as in term 1. What do you think our domain is for this? Do our x values start over here at -infinity? Are we getting any points over here? No. What is the first x value that we start with that we don't actually get to? 0. So our domain is going to be x values greater than 0, or if you want to use interval notation, parentheses 0 to infinity. So we start at the asymptote and are covered going to the right. But what about the range? All real numbers, excellent. We go all the way down. That graph is just going to keep slowly going upwards. So it's not leveling off horizontally. This is just going to keep shooting upward and outward. So our range is all real numbers or -infinity to infinity. Are you ready for an even worse mnemonic device? Here it comes. In this jungle, by this tree, we have a lion. Do lions have whiskers? Sure. It's a good video. A little smile. And that line says "rarn" for all real numbers. So these have a range of all real numbers. Exponentials have a domain of all real numbers. It's terrible. If it helps you use it, if you're like, that's stupid, I absolutely hate it, don't use it at all. But keeping this straight from what we did yesterday is kind of tough, and that's why going back and forth between them is going to be helpful. So let's go ahead and take a look at our next one. Are there any transformations? What's that 1/3 doing? It's the base. So there are no transformations. So where's our asymptote? It's vertical, and it's going through 0. So x equals 0 for our asymptote. Next, step 2, isolate the log. There's nothing more I can do to get that log all by itself, so we are ready to put it in exponential form. Log, big, animal, ears. And what are we going to use for the ears? Y instead of f of x. So my base is 1/3. My exponent is y. And my answer is x. So we've got an x equals equation. So we're going to go ahead and use those power values. So which column am I going to put values in? The y column. So we want to make this be equal to -1, 0, and 1. What's 1/3 to the -1? Give them both bad attitudes. It reciprocalizes the fraction. We get 3. What about 1/3 to the 0? 1. What about 1/3 to the first? 1/3. And that gives me my 3 points. And as we can see, this one is curving up towards the asymptote, closer, closer, closer. And this one is shooting outward. See if you can write the domain and range for this. Domain is x greater than 0. We're covered to the right of the asymptote. Or if you wanted to do interval notation, parentheses 0 to infinity. What's my range? Rarn for ranges all real numbers. So you can use the fancy R. You can write rarn if that pleases and sparkles. Or you can do negative infinity to infinity. And folks, I think I'm going to stop there before lunch. And what I would like you to be working on is in the homework packet. Hopefully you got done with 1, 2, 3, and 4 yesterday. The first 2 you could do by hand. These other 2, you can definitely use a calculator. This one gets nasty because of the 0.4. That one gets nasty with the 2 fractions, so feel free to plug those into your calculator to find the inputs and outputs. You can now do numbers 5 and 6. We haven't quite gotten to the page 2 stuff yet. As you look at page 2, what's different about those log ones? there's a lot more stuff. We've got transformations going on, which is going to mean we're going to have to isolate the log and figure out where the asymptote is. So that's what we're going to be working on after lunch today. On page 3, however, you can actually do 11 through 18. For 15 through 18, you will want to use your square sheet to figure out how to evaluate those logs. And I would just go ahead and put an equals X on all of these so that you know that that's what you're looking for in exponential form. So that's what you can be working on before we leave for lunch. And after lunch, we'll be working on those more complicated log graphing problems.